Hello everyone. Today we are going to talk about Chapter 7, an introduction to the solar system. In this chapter, we'll basically have an overview of the solar system. In later chapters, we'll talk about the detail of each member of the solar system. Let's first look at what are the most important members in the solar system. You can imagine we call it solar system. Of course, the sun takes a most important role in the solar system. Actually, if you look at the overall size and overall mass of the sun itself is 99.8% of the mass of the total solar system. And other than the sun, we have 8 major planets, 5 dwarf planets, and Pluto is now one of the 5 dwarf planets. And we have nearly 200 known moons and a host of small objects. You can see that all these objects, all the planets, dwarf planets, and other small objects, adding together, they only take 0.2% of the total mass of the solar system. If you put the sun and 8 major planets in scale, you can see in this picture, their size is in scale, but not the distance. You can see even Jupiter, the largest planet in the solar system, is still much smaller compared to the size of the sun. And among all the members of the solar system, humans have sent spacecraft directly to many of them. And we have sent probes to land on the surface of Venus, Mars, our moons, and the Saturn's moon Titan, and as well as several asteroids and one comet. And among all these missions, and the only members the human being set foot on is the moon. And in recent years, NASA is actually restart the mission to send people to the moon again. Other than the 8 major planets we know, there is a lot of members of the solar system you may not be familiar with. And the solar system, the overall size, is far beyond the furthest planet, Neptune. Now let's take a look at a short video to give you the introduction is how big is the solar system.
Space Place, in a snap. The solar system we call home has our sun, 8 planets, all their moons, the asteroid belt, and lots of comets. Outside Neptune's orbit is the Kuiper Belt, an almost empty ring around the sun that has icy bodies, almost all smaller than Pluto, making slow orbits around the sun. But what's beyond the Kuiper Belt? Beyond the fringes of the Kuiper Belt is the Oort cloud. Unlike the orbits of the planets and the Kuiper Belt, which are pretty flat like a disk, it's a giant spherical shell surrounding the sun, planets, and Kuiper Belt objects. Like a big bubble with thick walls around our solar system. It's made of icy pieces of space debris the sizes of mountains and sometimes larger. This is where some comets come from. The Voyager 1 spacecraft took 35 years to leave the sun's magnetic influence. It's traveling 1 million miles each day. At that speed, it will take 300 years to reach the inner layer of the Oort cloud. And then it will take 30,000 to get through it all. It's that thick.
You can see from the video, solar system is actually much bigger than you might think about. Now let's take a look at in a little bit more details what are the major planets and how we put them into different categories, and what are the dwarf planets based on their property as what they are made from and how far away they are from the sun. we actually put 8 planets into 2 categories. The first one is rocky inner terrestrial planets, which have Mercury, you can see, which is the closest planet to the Sun, Venus, Earth, and Mars. If you look at this category of planets, one of their shared common property is that they are very close to the Sun compared to the rest of the planets. Another common property you can see here, they are rocky terrestrial planets. So that also means they are primarily made from rocky material. And if you look at their overall size, you can see here the group. They're actually much smaller than the other 4 planets. So based on the size, we put the other 4 in one category. They are Jupiter, Saturn, Uranus, and Neptune. We call them gaseous outer giant planets. Just by the name of their category, you can see those 4 planets are huge compared to the inner terrestrial planets. And also, they are further away from the Sun than the 4 rocky terrestrial planets. They are made primarily from the gas, although you may not be able to see from this picture. And other than Saturn, Jupiter, Uranus, as well as Neptune, they all have rings, although it's not as significant as Saturn. And even beyond the orbit of Neptune, we have what we call icy dwarf planets. There are 5 icy dwarf planets, and Pluto may be the famous one. Pluto used to be a major planet. When I was at elementary school, I learned that there are actually 9 planets. But later on, scientists actually discovered similar objects, similar as Pluto, and a little bit beyond the orbit of Pluto. For example, Sirius, Eris, Haumea, Maker. At that time, there's actually a hard decision to make for the astronomy society, because the other 4, which are pretty similar to Pluto, either we include the 4 to be a major planet. So now we have 9 plus 4, we'll have 13 major planets. Or we can make our new rule to define planets. And turns out that the criteria set by the International Astronomical Union for our 4-sized planets are: first, it is in orbit around the Sun. The second, it has sufficient mass to assume the hydrostatic equilibrium. So that just means they should have a nearly round shape. And the third is it has cleared the neighborhood around its orbit. And under the new rule, Pluto unfortunately meets only 2 of these criteria, so the first 2. But in the region of Pluto, there's a lot of debris and small objects. So Pluto actually failed the third criterion. It has not cleared the neighborhood around its orbit. So therefore, the International Astronomical Union actually downgraded the status of Pluto to the dwarf planets. And also at the same time, they also put the rest of 4, which is beyond the orbit of Pluto with the similar size. They put all these 5 as the category of dwarf planets. And because these planets are very far away from the sun, the temperature is pretty cold. So they actually not only have rocky material, but they also majority of the planets also has water ice within it. Other than the major planets and dwarf planets, there are a lot of asteroids. They are basically rocky and metallic material. And asteroids are primarily located in a belt which we call asteroid belt between Mars and Jupiter. And we also have a lot of comets and which are made from frozen gases. Comets usually orbit far from the sun, and the comets usually come from the outer layer of the solar system, for example, outer clouds. And of course, other than asteroids and comets, we also have countless smaller grains of cosmic dust that is very, very small. And there are some asteroid that has name. And some comets, you may recall, they have name. And occasionally we can observe the comets when they get very close to the Earth. But there are a lot of asteroids do not have name. And one thing we may worry about asteroid is that when it gets too close to the Earth, we'll worry about if it will captured by Earth's gravity and finally will climb on the surface of the Earth. And the government even developed a defense system in case any asteroid or big asteroid may strike on the Earth in the future. The familiar picture may be like this. In the very center is the sun, and it is the major planets and the dwarf planets orbiting around the sun. In this picture, if you put the real size, or we call to the scale size of the planets and dwarf planets, they are almost invisible. Actually, the distance between planets are much, much larger than the relative size of the planets. The typical picture you see is that in order to fit all the planets in the picture, they usually scale down the distance between planets much more than the size of planets. And it may give us the wrong impression that planets are actually closer, but in fact, they are actually very, very far away from each other. Now let's take a look at the simulation. If we put the planets and their size to the actual scale, how far away each planet. You can see we can start from the Earth. So in this scale, the Earth is like a marble this small. Now let's go to the direction toward the sun. Let's go to the closer planets and in the direction toward the sun, which is Venus. So we can take a look at how far away is Earth from Venus. And remember, the bottom actually gives you an idea of the distance. So you can see it's mostly empty space. It really takes a long distance before we can reach Venus. And how about the sun? If we click the surface of the sun, now we start our journey from Venus to the sun. You can see we'll definitely pass Mercury first. You can see now we're finally able to reach the surface of the sun. Now let's reset to the Earth. So this time, we're going to travel in the other direction. So how about we set our destination to Saturn? You can see Saturn is not yet the furthest major planet in the solar system. Let's click on Saturn. So we'll start to travel from Earth to Saturn. You will see that the distance actually start to fly. It's just like we send a spacecraft to Saturn. So we start to fly from Earth, then we pass Mars, and then we first pass the asteroid belt. And before we reach Saturn, we'll have to reach Jupiter first. Remember, as we also mentioned, the outer Jovian planets, they are large planets, right? So they're even further away from the sun. You can see the relative distance from the sun. All 4 terrestrial planets are very close to the sun, but the rest gaseous large planets, they are all further away from the sun. So from this picture, you can see the Earth is just a small marble used to be at the center, right? And we already traveled so much distance. Finally, you can see we'll reach Saturn. And remember, we just reached Saturn. There is still long distance to travel to Uranus and Neptune. The true scale solar system is actually, you can see the distance between the planets is actually much larger than the actual size of the planet. Now I want to share with you a video, talk about a group of people. They actually built to the scale the solar system in a desert to demonstrate how the solar system really looks like.
If you look up an image of the Earth and Moon, you're going to get a picture where they're quite close together. Something like that. But in reality, the Earth and Moon are about that far apart. That is the Earth and the Moon to scale. Taking the same concept, but for the solar system, every single picture of the solar system that we ever encounter is not to scale. If you put the orbits to scale on a piece of paper, the planets become microscopic and you won't be able to see them. There is literally not an image that adequately shows you what it actually looks like from out there. The only way to see a scale model of the solar system is to build one. Welcome to Black Rock Desert. This is Alex. I'm Wiley. He's going to be behind the camera. I'm going to be probably making a lot of mistakes on camera. We have 36 hours to measure the distances, trace out the orbits, and set up a time-lapse shot from up on top of a nearby mountain. To create a scale model with an Earth only as big as this marble, you need 7 miles of empty space. So that's why we're here. Why did you guys come?
I don't have a job.
At this scale, the sun is 1.5 meters, so about that big around. So we are driving right now to Mercury, and we've arrived. Venus is the same size as Earth. I have the world in my pocket somewhere. And Earth. couple of robots rolling around on that one. Once the time-lapse is ready, we'll drive each orbit with a light. Hopefully you'll be able to tell just how big they really are. Onward to the outer planets. Jupiter. Saturn. That tiny light out there is our sun, just over a mile away. The sun's way, way out there now. So this is it. This is the edge of the solar system.
So right now, it's about 7 a.m. We just woke up right before the sun's about to rise. We are on the Earth's orbit. Wiley is over there holding our sun. Cue the dramatic sunrise music.
So if we've made our model correctly, your perspective from where Earth is on the model will match your perspective from standing on the real Earth. So if you look back at the sun, you will see that the model sun and the real sun are the exact same size. And that's how you can tell that the proportions are correct. There are 24 people in the entire history of the human species, billions of people, who have actually seen the full circle of the Earth with their own eyes.
Following the breakfast, the astronauts went to the suit room where they donned their spacesuits.
This is man's attempt to get to the moon.
0. We have liftoff. Liftoff at 7:51.
In Earth orbit, the horizon is just slightly curved. When you head on out to the moon, that horizon slowly curves around and upon itself, and all of a sudden you're looking at something that's very strange, but it is very, very familiar.
Oh my God, look at that picture over there. Wow, is that pretty?
You can put your thumb up, and you can hide the Earth behind your thumb. Everything that you've ever known, all behind your thumb.
Not any bigger than that, way up there.
It's really beautiful. You can cry.
That's what I really wanted to try and capture. We are on a marble floating in the middle of nothing. When you sort of come face to face with that, it's staggering.
I hope you enjoy watching that video. You can see this is not very easy to build a real scaled model of the solar system. And if you think about that, within the video, we actually scale down everything of 1 billion times. If that model represents the real solar system, where would the nearest star be? If we keep the same scale, the closest star would be tens of thousands of kilometers away. If you build this scale model in the city, or like in the video that in the desert, you would have to place the representation of the stars on the other side of the Earth or beyond. So you can see between those major objects, that's primarily empty space. You may wondering, we actually know a lot about the planets in our solar system. For example, how far away they are from us, how long they rotate around the sun, and how big they are, and how heavy they are, as well as the density and what they are made from. Although luckily we do get some direct measurement by sending the probe to some of the planets. But even before we do that, we actually have a better idea of the property of the 8 major planets. I hope you still remember what we learned from a previous chapter about Kepler's laws and Newton's laws. We're actually able to get the distance of the planet from Kepler's third law, because we can observe the revolution period. That is how long it takes for planets to orbit once around the sun. And this period have a relation with the semi-major axis, or the average distance of the planet to the sun. So therefore, we can get distance from Kepler's law. And the diameters we can know from the observation, because we know how far away they are, and we know how big they appear to us when we look at them from the telescope. Then we can calculate their diameter. For the masses, you may still remember about Newton's law. And by combining Newton's law and Kepler's law, we're able to determine the mass of these major planets. How about the density? The density, we can, if you still remember, it's also written here, the formula to calculate the density. Density actually equals mass divided by volume. And the volume, we can always approximate the shape of the planet to a perfect sphere. So therefore, by knowing the radius of the planet, we can calculate the volume. And with knowing the mass and volume, we can calculate the density of the planet. And the density value will actually give us some clue what the planet is made from. Just give you some reference. The average density of the air, for example, the air on the surface of the Earth, is about 1.3 kilogram per meter cube. The density of water is about 1,000 kilogram per meter cube. The rocky material, although we have different types of rocks, but on average, they are 2,600 kilogram per meter cube. And another very important material we believe that make up the planets are iron, which is about 7,900 kilogram per meter cube. So if you look at the density of the material, we're able to calculate by using this equation. We actually will have a little bit of idea on what they are made from. You can see the density, for example, the density of the Earth is over 5,000. So you can see that if the Earth is just made from the rocky material, the Earth should have a density around 2,600, not too much bigger. However, you can see Earth's density is much more than that. So you may know that the material actually have a common material actually much higher density than rock or the iron. Actually, later on, you will learn that Earth also have an iron core. And for the giant planets, the outer gaseous giant planets, you can see their density are much smaller than the terrestrial planets. Just by those values, you probably know that they cannot just made from rocks or irons. There must be a material which much less density, which make a significant percentage of the overall mass of the outer gaseous giant planets. A very interesting number I want you to take a look is that the Saturn's density is actually only 700 kilogram per meter cube, and which is even smaller than the density of water. If you remember we talk about float or sink. That also means if you have a container big enough filled with water and big enough to put the Saturn in, Saturn will actually float on top of water while the rest of the planet will sink down to the bottom of this container. As we already talked about, the value of density actually contains a lot of very important information. So therefore, I want to show you an example on how to calculate the density of the planet. And this not only applies to the 8 major planets in the solar system. We can use the same method to calculate the density of newly discovered exoplanets or the moons. So this way, by looking at the density, we know what kind of material they are made from. If they are made primarily from ice or rocky material or the gas. I want to take a Mercury as an example. So I copied some number from previous slides. The mass of Mercury is 3.3 times 10 to the 23 kilogram. And the radius, which is r of the Mercury, is actually its diameter divided by 2. The Mercury's diameter from the previous slides is 4,878 kilometer. If we divide by 2, which give you 2,439 kilometer. If we rewrite that into scientific notation, that is 2.439 times 10 to the third kilometer. But we want our units for the density is a kilogram divided by meter cube. So therefore, we'll need to do one more step to convert kilometer to meter. So you know that kilometer is a 1,000 meter. So we basically need to multiply 10 to the third power again. So which result into the 2.439 times 10 to the 6th power meter. Then we can do our calculation. So you can see this is a formula to calculate the volume. So volume is equal to 4 divided by 3 times pi. We can use 3.14 and times the radius, the cube, which is 2.439 times 10 to the 6th power, then the cube. You can definitely do the calculation. If you do the calculation correctly, you will roughly get 6.191 times 10 to the 19th power. The units is meter cube. Now we can plug in the mass number divided by the volume we just calculate out, which is 3.3 times 10 to the 23rd power kilogram divided by 6.1 times 10 to the 19th power meter cube. Which is equal to about 5.4 times 10 to the third power kilogram per meter cube. If you want to see if it's not in scientific notation, it's about 5,400 kilogram per meter cube. So that is actually how we calculate density, by knowing the mass and the radius of the planet. If you look previously, which exactly match what we had for the density of Mercury. Since we just talked about how by looking at the value of density, we can have a brief idea what is the composition of the planet. For example, if you remember, we talk about the Earth. Earth's density is just too big for just rocky material. So we know the Earth also has a significant part of iron. And now let's take a look at the detail. What is actually composition and the structure of the planets? And the giant planets, they are actually primarily of hydrogen and helium, which is similar as the sun or most of other stars. And we believe that they all have the core of heavier rocks, metal, and ice. Because if you only look at if there's only made from the gas, even if the gas under very high pressure, the density of the giant planets, you can see from previous slides, they are all three of them are all over 1,000. They're actually much larger than just the air. So we believe that underneath the thick layer of hydrogen and helium gas, there must be the material have very high density. And remember, all these planets, when they formed in the same environment. So they will gather the similar material from the same environment. Because you may have heard about the Earth actually have our metal core, is iron core. We also believe that these giant planets, underneath the thick atmosphere, a thick layer of the gas, there must be a core with heavier rocks, metal, or ice. And because the hydrogen and helium gas, they're pretty fluid. So therefore, those rocks, metal, which has higher density will have a chance to sink all the way toward the center due to the gravity. But unfortunately, even the probe we sent to Jupiter, it's lost the communication with Earth when it's still falling through the atmosphere of Jupiter. So that means still in the part of Jupiter that is still gas, and not able to reach what we believe the rocky or metal core. So this information that we don't really have a direct first-hand evidence, but based on how the planet forms and based on their density, we believe they have like a solid rocky and metal core. And unlike the terrestrial planets, all the giant planets, they have rings. Even Jupiter has a very thin ring. On the other hand, if you look at the terrestrial planets, Mercury, Venus, Earth, and Mars, and just looking at their surface, they are actually rocks. And we all already know their density is much more, especially for Earth, is much more than the average density of a rock. So we believe they also have a metal core. It's actually iron core. But unlike the giant planet, terrestrial planets now is a solid. And even if you put a piece of heavy metal on top of a solidified rock, it won't sink down. So if you want the heavier material to sink down, you're going to have something as a liquid. And we believe at the early stage of formation of the terrestrial planets, due to the bombardment, the collision of a lot of debris and the planetesimal, those terrestrial planets are once molten. So that means they are very high they have very high temperature. All the rocks used to be lava. So at that time, it's actually allowed what we call the structure to differentiate it. Therefore, the denser material able to send all the way to the center and later on become the metal core or even higher dense core of the terrestrial planets. But this already happened long time ago. Because if the terrestrial planets, they are all solid at the beginning, there's no way those dense material can gather or concentrate at the very center. So you can think about an example I can give you is that you may get some like muddy water from the nearby pond, and if you let the water to sit for a while, all the heavier like mud, they will all go down to the bottom of a container and left the clear water on top. And if this already differentiated muddy water and experience extremely low temperature, everything will freeze. So the water will become ice, but the mud, which is already sink down all the way to the bottom, will still be there. So it will be the similar as what we talk about for the terrestrial planets. And for the moon we are talking about is the only moon of the Earth. We believe the moon is similar as terrestrial planets, probably made from a rocky material. However, most of other moons, for example, the most of the moon actually coming from the outer giant planets because they are very, very far away. And we actually, remember, we can use their mass and the volume to calculate their density. And other than the rocky material, those moons, they actually, we believe they have larger quantity of frozen water ice. There's a couple of reasons to contribute why the inner planets and the outer planets look so different. Why the inner planets are so small but the outer planets are so big. And why the moon in the region of outer planets have a larger quantity of frozen ice, but the moon, our moon, actually mostly a rocky material, can be explained by the distance they are away from the sun. It is pretty straightforward that objects close to the sun will receive more energy from the sunlight. So therefore, they have a higher surface temperature overall. Just give you some examples. So Mercury, the side of Mercury facing the sun, can be as hot as 218 Celsius to 413 Celsius. So it's very, very hot. But if you compare that to the Pluto, which you know is even further than Neptune to the sun, which is actually quite far away from the sun, you can imagine it receives very small amount of energy from the sun. The Pluto's average is only about negative 220 Celsius. And you can imagine the inner planets, the terrestrial planets, they can experience pretty high temperature. So therefore, you can imagine those gas like hydrogen and helium, they will pretty much run away into the space. And only primarily rocky material and metals, they can bear this high temperature, right? And as well as water. You can see for the water, if the temperature is so high, it won't exist as ice or liquid water. It will become water vapor and become air. Then it's easier for the water vapor to just escape into the space. However, if you look at the planet of the moon that's further away from the sun, their temperature is much lower. So therefore, the water can survive on their surface as water ice, and as well it's easier to keep like hydrogen and helium, those gas and around. You can see here from this perspective, Earth is actually at exactly the right distance away from the sun. If the Earth is too close to the sun, it will be too hot for a human being to survive. If it's a little bit further away from the sun, further away like Mars, it will be too cold for us to survive. So therefore, Earth is actually, we only have one Earth, and Earth is exactly at a condition that's suitable for the life to sustain. And after the initial formation of terrestrial planets, the surface of terrestrial planets has been modified by impacts from space and by a lot of degrees of geological activity. For example, you may remember or see later on there was a lot of craters on the moon and on Mercury. This is due to impact of small objects. And you may know that on the Earth surface, we have tectonic activities, volcanism, and though all those geological activity are actually able to modify the surface of terrestrial planets. Next, let's talk about how we're actually able to dating the planetary surface. How we know how old is a surface and how old is a planet. We'll talk about the two primary way we can determine the age of the surface. So remember, this age will not necessarily talk about where all the material first appear. We'll basically obtain what we call the time since the rock last solidified. And the easier one, although it might not be that precise, is counting craters. The reason why the counting crater can provide the idea how old is the surface, because we all believe that the heavy bombardment period happened at the early stage, like right after the planet's forms. So in terms of time, it's a very, very, very long time ago. Then the bombardment period already stops for a very long time. If the surface still have a lot of crater, we can safely speaking, the surface does not really change for a very, very long time. So that's why we can define the surface as older. So this basically the time since the rock last solidified. So remember, this is a picture of the far side of the moon. You can see here there is a lot of craters on the surface of the far side of the moon. Do you think we have a similar amount of crater on the surface of Earth? Probably not, right? So therefore, because you can imagine Earth actually have a lot of geological activity, the volcanism and tectonic activities. So therefore, we can conclude that Earth's surface is actually younger than the surface of the far side of the moon. And another way we can dating the planetary surface is by looking at the radioactive rocks. So this way we can obtain the time since the rock last solidified. And by using the radioactive rocks, we can estimate the age of the moon and the Earth is about 4.5 billion years old. So what is radioactive rock? The radioactive, they always contain what we call there is a radioactive element. The radioactive element actually will decay. That means they will become new element within a certain time. And we actually use a very important term of half-life of radioactive element to measure like how fast the radioactive element decay over the time. So the half-time is pretty much the time it takes for half of the radioactive element to decay. Of course, there are some will decay sooner and some will decay later. So I actually have a simulation which can help to understand a little bit of what is half-time. Now, if you look at the simulation, here is the radioactive element. Remember, they are all individual atoms. So they are not yet decayed at all. So you can see none of them decayed. So let's start with a larger half-time to see how the half-time actually works. We'll play the simulation first. You can see gradually the red turn into blue. That means the radioactive element to start decayed, therefore become a new element. You can see the half-time does not really matter how quick individual atom actually decayed. It actually matters in a group. Let's reset. How many times it takes half amount of atom to decay to become another element. So that is actually a measurement of half-time. So you can see if it's a smaller half-time, you can see that means more element will decay with short amount of time. And the larger time or just means less number of atoms will decay within a certain time. Now let's take a look at how can we use half-time to actually date the planetary surface. We can basically measure what we call the remaining percentage of radioactive element, or we can measure the percentage of decay product. For example, if we measure there actually only half of the radioactive element remain, we know it's exactly past its half-time. For example, if we use uranium, if we measure the abundance of uranium is actually become half, we know it's actually the half-life past, which is 4.47 billions of years. And if the time goes even further, for example, now there's only 1/8 of radioactive elements left in the sample. So we know that it's already goes through 1, 2, 3 of the half-time. So that means the total time should be 3 times the half-time. So this way, by looking at how much percentage, how much fraction of the radioactive element actually left inside the sample, we're able to date the planetary surface. And you can see that the planetary surface is about billions of years old. So therefore, we should pretty much select the radioactive element has a comparable half-life. For example, samarium, which has the longest half-time, 106 billions of years. And the rubidium also have pretty long half-time. And the thorium, uranium, and the potassium, which always also have a half-time, which in terms of billions of years. So they're all very good to actually date their planetary surface. However, there are some other radioactive elements which actually have much shorter half-life. For example, I'm not sure if you heard about the carbon-14, which is also a radioactive element to date. Actually, archaeologists use carbon-14 a lot to date the age of the fossil. So carbon-14 actually have half-time about 5,713 years. So you can see use carbon-14 to date the surface of the planets. It's just too short, right? If you wait a billion years, you almost cannot detect any carbon-14. But you use it to date like a human remain from the early civilization, it will work just fine because the time span is roughly comparable to the half-life. So therefore, archaeologists have long used carbon-14 to date of certain objects. You probably heard about like the lives on the surface of Earth, at least like a human being, like animals, we all carbon-based life. So we actually have a lot of carbons in our body. And once the animal, they're actually living, they always eat food, they have metabolism. So they always exchange carbon with the environment. So they are carbon-14. The abundance of carbon-14 is pretty stable. So you can think about that it's pretty much the similar as the environment. However, after the animal die, it will no longer exchange the carbons with the environment because it won't eat anymore. So for example, inside the bones, the carbon-14 will start to decay, so gradually become less and less. So the moment the animal, or for example the bone, no longer exchange carbon-14 with the environment, that's the time we date. We're starting the time. So for example, you, the archaeologist, found a bone belong to an Asian animal, then they can basically look at how much percentage of carbon-14 left inside the bone, compare what should be the standard percentage of carbon-14. We can basically date how long ago was the animal die. So you can see if it's like become half percent, like 15% of carbon-14, you can see the animal pretty much like died about more than 5,000 years ago. And so therefore this carbon-14 radioactive element are good applied to organic remains like animal bones between 500 to 15,000 years old. And on the other hand, if you want to date the surface, like planetary surface, which is much older, we're gonna have to select the radioactive element which has much longer half-life, which in the range of billions of years. And then finally, let's talk about the origin of the solar system, where the solar system is coming from, why it's become how it looks like today. And unfortunately, there's no time machine for us to travel all the way to 4.6 billion years ago. So there's no way we can observe the events directly. Even if we can observe, the formation of the solar system actually takes millions of years. It's just too long for a human being. However, we can get some clues on how the solar system forms by looking at the property of the planets in the solar system, as well as the entire solar system. So we pretty much know that all the planets lie in nearly the same plane and revolve in the same direction around the sun. It's like pretty much the disk. And the sun also spins in the same direction around its own axis. So from this, like the rotation, the same direction rotation of the spinning as well as orbiting around the sun, we can pretty much confirm that the solar system will coming from something what we call the solar nebula that's already start to rotate around the center when it start to form. And the composition of the planets actually give another clue about the origin. We already know the inner planets and most of the asteroids are made of rock and metal, which can survive heat, but they contain very little ice or gas. However, in the outer solar system, where it has always been cooler, the planets and their moons, as well as icy dwarf planets and comets, are composed mostly of ice and gas. So from this clue, we can pretty much have an idea that those objects are pretty much gather the raw material from the same environment. Why they end to have different material at end, it really depends on the temperature, like how far away they are from the sun. And the other clue is about the other planetary system. Although unfortunately we cannot observe the formation of our own solar system, but if we look at the space, we look at the universe, there are actually a lot of stars is actually in the formation stage. So they are forming their own planetary system. And we're able to capture a lot of pictures. You can see a lot of them actually have this, what they call the nebular structure. So that means the planetary system most likely originate from a nebula. And some of them you can see from this picture, maybe in a later stage of the formation. You can see from the side view, they form like a disc shape, which actually established the overall shape of our planetary system. You can see a planet pretty much orbit around the sun on the same surface, like a disk. And therefore, we believe the sun and the planets, they actually form together in a giant spinning cloud of gas. And the direction of spinning and later on inherited by the sun and its major planets. And these clouds contain gas and dust. And this will later on become the raw material to form the planets and the sun. And we actually call this big spinning clouds of gas solar nebula. And you can see similar circumstellar disk around other stars can be observed. So it's basically give us the idea of the solar nebula at some time. At the beginning, it's maybe a little bit irregular shape, but as the spin and the spin is actually become a disk shape. Now I want to share with you like a video why some object like a big clouds, we call solar nebula, with a fast spin, why it can become a disk shape. Now I'm going to play this video. I want you to pay attention to the lady's skirt. You can see at the beginning, the skirt is just down. When the lady to start to spin, you can see the skirt actually make a disk shape. That is exactly what happened to the solar nebula. You can see from the image, the solar nebula at beginning may have more like irregular shape like a cloud. But as it's spinning faster and faster, you will basically make the cloud turn into a disk shape. And remember, that is still a time there's still like losing a lot of like debris inside the solar nebula. And how the planets actually form. we believe that material actually first coalesced into planetesimals. Planetesimals that is pretty much, they're not enough to call planets, but this is like a seed later on grow into a planet. Then those planetesimals, they actually gather together to make the planets and moon. So they basically, through the gravity, so they can collide with each other, then they become one, or they just attract nearby small debris or material to grow in size. And the material that are not become a part of a planets or moons and just left inside the solar system, and they become comets and asteroids. And I also want to share with you with a video gave you a little bit idea how the planetesimal can actually grow bigger and bigger, then later on become a planet. So I actually use this cotton candy machine. So you can see once the gentleman put a paper corn and the cotton candy start to pick up the material right inside the environment, you can see clearly it start grow and bigger and bigger. So that is what we think, how the planets grow in size and finally become a planet. And we pretty much believe almost all the planetary systems have formed in a similar way. First spin, form a disk shape, then the material get together to form planetesimal, then grow in size when they combine each other or when they collision with other material and the material become part of them. However, after the planetary system forms, they probably have evolved differently, have different evolving paths. And for example, if you look at the spinning of Venus in the solar system is not in the same direction of the other planets. And we believe that might be due to a more random process of impact and collision in the early solar system stage. So we believe this collision period, which happen mostly randomly, makes the planetary system evolve quite differently. That is all what I want to talk about for Chapter 7. In Chapter 7, we first overview the members of the solar system. We talked about the major planets, the dwarf planets, and the asteroids and the comets. We also talk about the difference between them, and we actually how we get a measurement of them, and as well their composition and the structure. Then we talk about we can count the crater and use the radioactive elements in the radioactive rocks to date the planetary surface. And finally, we briefly talk about the origin of the solar system.